All right, we're going to get started. Thanks everyone for coming out to the DeepSpeed Meetup. We're really excited to see you all. My name is Tunji. I lead the DeepSpeed team at Microsoft. And I guess here there are a variety of folks, from those who actually use DeepSpeed every day, or folks who never heard about DeepSpeed before. Maybe you came here just because the name seemed very cool. And I heard someone call it the coolest palindrome they know about. So if you've never thought about that. But yeah, we have a great series of talks today. But before we get started, I just want to say a big thank you to LinkedIn for hosting us, to Animesh in particular for making this happen. So if we could give him a round of applause. Yeah, we're really excited. So we'll get started right away, and Animesh will take us away. He has an exciting talk, so please stay tuned.
Thanks, Tunji. Hey, thanks all for being here. Definitely thanks a lot to you, Tunji, for being a great partner for the course of last 1.5 years, right, as we've been venturing down this journey. So very quickly about me, my name is Animesh. I lead the distributed training team within LinkedIn. And, I'll be quickly going through some of the stuff here, right, and get to the real presenters who will be talking about, some of the exciting work, not only happening here, but, in some other companies as well, using DeepSpeed technology. Just to specific, our relationship with DeepSpeed, this is something we established around 1.5 years ago, as we saw the needs in the industry increasing, right? And I think most of you will remember it was the same time, around November of 2022, when the whole ChatGPT explosion happened, right? And AI before that and AI after that is very different, right? The scale at which you are thinking, the kind of models you are planning, the use cases you are envisioning, they have a totally different ring to it, and that's where the scale becomes a very important factor. Very quickly about LinkedIn, right? One of the key missions in the North Star for LinkedIn is to create economic opportunity for every member of the global workforce. The LinkedIn ecosystem, the LinkedIn network is pretty big at this point. We have 1 billion plus members on LinkedIn, more than 67 million companies, multiple products and skills. The core data structure is a graph, right? When you combine this, there is a lot of solid engagement happening on LinkedIn, people sharing knowledge, people sharing news, content, and the platform is growing exponentially. A bit about the large models. I think most of us here have seen this happening over the course of last year, right? I think with LLMs, it's very clear the scale at which the size of the models has been increasing. You follow the industry, you are seeing, starting from the millions to 7 billion to 70 billion to 180 billion to 500 billion, now trillion tokens, right? The size of these models have been growing exponentially. And not without reason. I think it's very clear the reasoning capabilities of the models are much better if the size is bigger, right? There are a lot number of use cases you can get done with smaller models, but as models are getting bigger, they're able to reason better, right? And that's where, the thrust and the momentum is there. But it's not only LLMs. Within LinkedIn, we are also seeing a lot of use cases around graph neural networks, right, which are exponentially growing in size. Our traditional models, a lot of them which are on TensorFlow, they're also growing in terms of the complexity of the architecture as well as the size of parameters. So the effect is all around. Any kind of model you pick up, right, it's becoming bigger. The architecture is becoming more complex. That also means that, there are a bunch of more pressure on the infrastructure, on the compute requirements. I mean, obviously, as you see the graph, I think one of the biggest models was Megatron, Turing NLG, around 500 billion parameter. But now, based on the current data, which is out around GPT, the latest is 1.8 trillion tokens, trillion parameter model, right? So This kind of model training, specifically on the model training architectures, right, it's putting a lot of pressure. And there are different ways to achieve that, right? Hardware definitely plays a role. If you look at some of the models which have been trained, there are different mechanisms. So someone used V100s. There's the first generation of NVIDIA GPUs, right, which became very popular. Within LinkedIn also, we started on that same journey. But if you see the amount of V100s which were needed to train GPT-3, 10,000 V100s, right? Like you definitely need to have an infra of that particular scale, or you need to compromise on the amount of time, right, you are willing to take to train a model. Now, if you flip, for example, with OPT 175 billion, right, that was done on 992 A100s, and that took just 33 days. So it's a constant, trade-off between the amount of hardware, the amount of time, the compute, and the data size, right? Like, I mean, the two parameters which typically come when we are discussing requirements on the compute side is how many tokens, what's the throughput you want in terms of tokens per second, what's the size of the model, right? And these are governing factors, how you are architecting your underlying infra. Obviously, at the heart of it, whole explosion is the transformer layer, right? Which is essentially a lot of effort in terms of, preparing your data, creating the tokens, and ensuring that you can get the data to the GPUs fast enough. But a lot of the latest advancements have been possible with the encoder-decoder architecture which Transformers brought, right? And that exactly was the same thing which was used to train GPT models, right? And then another technique which has become very popular, and even if you look at ChatGPT, it was a fine-tuned version. Fine-tuning has been one of the key things which has been repeatedly being done over the course of last year. A lot of people are taking the bigger models or the smaller models, going through and fine-tuning, and the results are stellar. I mean, ChatGPT, which is a fine-tuned version of the GPT 3.5, right, was the first one to explode on the scene and show the actual power of what you can get through fine-tuning. Though the scales are very different. I think in last year we were focused a lot on fine-tuning within LinkedIn. But when you are fine-tuning, the number of parameters or the trainable parameters are very, very small as compared to something like, when we are doing full parameter fine-tuning. So if you take a Llama 70 billion, it's 0.65 billion when you are doing LoRa-based fine-tuning versus, the full class of 70 billion parameters, which you have to go through. So the infrastructure scale requirements for full parameter fine-tuning are similar to what you will do for training. And definitely hardware is critical. We have a very solid GPU infrastructure in place within LinkedIn. We started a journey with V100s. There is a huge cluster of A100s currently in place. And then, we are setting it up with H100s, which are being racked up as we speak. So a lot of focus on getting the right hardware, because to scale at that particular level, right, you need to have the right infra in place. One thing which we have also noticed is the scale may not be linear, right? You cannot expect if I will get 80 GPUs instead of 8 GPUs, I will get 10x speed improvement. A lot of our analysis is showing that beyond a certain size, you will start getting linear improvements, but you have to scale out to compensate for all the network communication bandwidth. So going from 1 to 2 to 3, you might get similar performance if all your 8 GPUs were on a single node versus spreading out to 24 GPUs on 3 nodes. But a lot of benchmarking, a lot of work being done to ensure that we are able to do that. And hardware is not the only thing, right? And that's where technologies like DeepSpeed become very critical, because you can scale only to a certain extent using the hardware and the network, and optimizing your data I/O pathways. So then the techniques which become paramount for you to scale are things like data parallelism, model parallelism. We have been experimenting with tensor parallelism, right? So we are combining DeepSpeed libraries with Megatron to push the boundaries on the tensor parallelism. There are techniques like, there are different stages of, zero, which DeepSpeed has brought in, right? Which enable you to do different quantization techniques, and 0++, which allows you to use constrained network bandwidth environment, where you can take quantized weights and gradients and send it for distributed training and be able to operate in that constrained bandwidth. And that has been the fulcrum of our partnership with DeepSpeed. We have been leveraging DeepSpeed heavily throughout our training mechanisms, using all the different techniques like 0.1, 0.2, 0.3, right? So we are able to partition the weights, the memory, the gradients, and latest with 0++, we just saw a 2x improvement in speed after enabling it on one of our networks, and the team coming after me will be talking, some in detail about that particular work. Even in the fine-tuning work, DeepSpeed has launched RLHF capabilities, right, which can be used for folks who are doing reinforcement learning with human feedback. Those libraries are available and present as part of the DeepSpeed. We have enabled it within LinkedIn as well. So check it out. So in short, if we go through the layer, like there are investments on all these different layers we are making within LinkedIn and building a distributed training infrastructure, right? Starting from the hardware, right, going into the storage and memory, looking at techniques like RDMA and others so that we can speed up network. You move up, there is the compute layer. Our distributed training infrastructure runs on top of Kubernetes. We are at a scale where we need to span on multiple Kubernetes clusters. So a lot of investment going into that, a lot of investment going into scheduling strategies, gang scheduling, priority queuing, preemption, so as to make sure, our distributed training scheduler can scale as the training is scaling. And then on top of it, right, all the distributed training software we use. We leverage Horoword a lot for distributed TensorFlow training. DeepSpeed, as I called out, right, in the context of LLMs and PyTorch, we are leveraging heavily. With GNNs, we are, bringing a deep GNN, and a lot of the fine tuning is coming from the Hugging Face ecosystem. And at the very top, all the optimizations, right, which you leverage from all these libraries, right, including the things I talked about: data parallelism, tensor parallelism, 0++, BEFT, LoRa. But that's our top-down architecture, how we are scaling our distributed training within LinkedIn. And there are strong ambitions. Some of the team will talk about, right, the models we are training and the techniques we are using. And very quickly, one more last point, right? Since we are talking about generative AI, there is one more part of generative AI, which is, the application development world, where you are dealing a lot with prompts, right? LangChains, LLM agents. And there is quite a bit of exciting work happening within the team in that landscape as well. Of late, we have started looking into building a distributed multi-agent management framework where you could actually have agents participate, coordinate, and do goal-oriented action planning. So very, very exciting work happening on that front. If you're interested, do talk to me offline, right? I'll fill you in with details. And obviously in open source, as you are seeing right now, there is quite a bit of great explosion happening in this space as well. A lot of open source projects are coming. Microsoft itself has launched AutoGen. There are other products like AutoCrew and others which are coming. But this is one area where we see, at least within this year, there will be a lot more advancements where people are using autonomous agents, using LLMs. So we do expect to see a lot more load on these distributed training systems as these new use cases of building generative AI applications come through. So with that, I will call on Byron and Yun to talk about some of the work they are doing within the team in terms of scaling out our distributed training infrastructure.
Hi. Hi. Yeah, so I'm Byron. You can also call me Pinglen. And this is Yun. And we have Tao and Hamid and Tejas Halwan on the seat. Yeah. So yeah, thanks Animesh for the introduction for our overall stack. And in this talk, we'll dive into how we scale LLM at LinkedIn with the help of DeepSpeed. And particularly, we'll focus on 0++. This is the state-of-the-art algorithm for distributed training. Yeah. So this is a very high-level overview of our LLM training platform at LinkedIn right now. So I'll explain from the bottom to the top. So at the bottom, we have Kubernetes to orchestrate all the container. And you can have different image and different network setup for distributing training for that or inference. And on top of Kubernetes, we have flight to orchestrate for different kind of workload. For example, some workload are running data processing on Spark, and something are running inference on Ray, and something are running DeepSpeed on maybe PyTorch distributed. And on top of PyTorch, we have on top of Flight, we have PyTorch. Hi. Okay. Yeah, on top of Flight, we have PyTorch as our single training framework. So I guess everyone already know PyTorch. And on top of PyTorch framework, we have different kind of library for user to more easily implement or experiment with their ML workflow. And we have Hugging Face, a very powerful library for it provides very good channel or inference stuff. And we also have PyTorch Lightning, which is a very flexible framework if you want to write your custom training loop or stuff. And more importantly, we have DeepSpeed here. So DeepSpeed is for, we mainly use for two use cases. The first one is distributed training, and the second one is FastGen. We use that for inference. And we have all kind of popular use case for LLM right now. We have pre-training, we have fault perimeter fine-tuning, and we also have PEPT. Yeah. So this is the overview of Zero++, which is the state-of-the-art algorithm right now. So yeah, so I guess everyone already know a bit about Zero. Basically, Zero is a very legendary algorithm of distributed training. And this is a high-level overview of Zero. Basically, on the forward pass, it will do an all-gather first to gather all the weight together, and then do a forward compute, and then partition the weight again. So each layer at a certain moment won't hold the full perimeter. And on the backward path, it do the all-gather again, and do backward compute. And then after backward compute, it do partition. And after forward and backward are done, it start to do reduce scattering to reduce the gradient to different partition. And then it do the optimize step. But the problem is that under a certain scenario, the interconnection between different machines is actually slower than the connection under the same machine. For example, you have two machines and each machine has 8 GPUs. So within the same machine, the connection is pretty fast. But within different machines, the connection might be slower. So DeepSpeed team proposed Zero++, which basically tries very hard to reduce all kind of inter-machine communication. So the first method that proposed is to reduce the all-gather in the forward path. And how they do it, it basically quantize the weight to INT8. And this can cause 2x reduction. And the next one is to reduce the combination for backward all-gather. And they instead of spreading all the weights to different machines, they keep the weight under the same machine. So they don't need to do communication between machines. And this can cause zero cross-node communication. And the third one is backward pass gradient reduce scatter. When they are communicating between machines, it quantizes the weight to INT4. So this can cause 4x reduction. And in order to fully validate Zero++ algorithm, we have we prepare a low capacity hardware which has slower interconnection between machines, but faster interconnection between GPUs. And when we are running the experiment, we found some caveat for Zero++ algorithm at that moment. So for the first one is QWZ, that was for forward pass. And because most of the model right now are using BF16 kernel, but at that moment, BF16 kernel is not available on the open source version. And the second one is QGZ. So QGZ is quantized gradient, and we were hitting some tensor shape error at that time. So basically, the issue is that if you use like 3 nodes or 5 nodes, you'll hit some weird issue because they made some assumption on the tensor shape. And the third one is HPZ. So HPZ is the algorithm that trying to keep all the weights under one machine, but we're hitting some very mysterious and interesting NAN issue, and we will talk about that. So that's a very lengthy debugging process, and it's quite complex. So stay tuned for that. Okay, I'll hand over to you.
Yeah, thank you very much for the introduction. So as Baron has already said, like at the very beginning, we were hitting some issue enabling hierarchical partitional parameter, hierarchical partitioning. And the initial observation was that the loss is just gonna turn into not a number. And because you all know that like debugging not a number loss issue is like quite lengthy because the NAND can occur in everywhere. It can be NAND during the forward pass computation, so that even out of some not NAND activation or not NAND wait, you still got a NAND loss. Or it can also be NAND during backward communication, so that you kind of get a gradient with NAND and you update the model parameter with NAND, then your model parameter gets NAND as well, leading to your loss become next in the next iteration. And thirdly, it's also possible that the NAND is happening during the optimizer step, and then similarly leading to a NAND model weights that further lead to a NAND loss observation in the next iteration. So like the first thing you typically do is to like try to add logging here and there to see what's the first place that the null number issue take place. And just know that the problem we're hitting is actually a very, very, very niche edge case that only occurs at perhaps a very particular kind of setup with particular kind of model with particular kind of sequence length, etc. But the observation we had at the beginning is that the non-number issue is happening before you start to do the altogether during the backward pass, and after the forward pass has done. And just to give a more sense about how 0++ work here is that after the forward pass is done, it discards the we call it primary partition, where the model parameter is partitioned across all the GPUs in the world. And then it produces a secondary partition where the model parameter is replicated on each node, but sharded across the GPUs within the same node. And then, yeah, this is when, after the second partition is done and before we start all gathering for the intranode partition, this is where the NAND happens. And we, after some investigation, we figure out that, yeah, it's probably, it's very likely to because that, as I said before, there involves a step of creating a secondary partition by like potentially copying some data from your full tensor into the secondary partition placeholder. And then after the memory copy, you do the altogether. And because the memory copy is device to device, which is by nature asynchronous, and it's possible that you just launch the altogether CUDA kernel before your actual D2D device to device memory copy has actually finished. And that's probably gonna cause a problem because prior to the data mem copy finish, the original data of your placeholder for the secondary tensor probably can involve some random pointer that can easily point to some NAND, point to some memory space that's gonna be interpreted as NAND. So yeah, and we've tested that to figure out that this is indeed the case. And the solution is just to just add a CUDA synchronize to make sure that the DTD mem copy is indeed finished before we kick off the altogether CUDA kernel. and that actually solved the issue. And yeah, like we were able to like contribute some PRs to Zero repo, and I think both of like the whole team just felt contributing to GitHub DeepSpeed repo is really interesting experience, like reading the DeepSpeed source code and understanding how the system actually works under the hood. Yeah, it was a blast experience for us. And yeah, and just during the investigation and performance profiling, while we were also finding some interesting observation that probably can be useful by sharing with the community, which is like in some data center setup where you're possibly using TCP, like you're not using InfiniBand, and your TCP is kind of not able to be saturated by a single TCP flow. Like your NIC bandwidth cannot be saturated by a single TCP flow. This kind of scenario can be like gigantically improved in terms of the bandwidth by having multiple independent NIC operations happening in parallel. Like it's probably not going to have a lot by increasing the number of parallel threads for number of parallel like channels, or say socket threads for each NIC operation, because each single operation is still a synchronous one, and it has to maintain some synchronous. It has to be have some synchronization within each kernel. But having multiple independent NIC operation actually helps a lot. And if this is the case in this scenario where you decide to improve the overall step time performance by increasing or say by enabling prefetch in DeepSpeed, where you kind of have a different stream doing the parameter altogether at the same time of doing, say, for example, gradient reduce scatter in the backward pass. And if you have already done this and you try to enable either creating a gradient quantization or hierarchical parameter partition for the backward pass, and you just enable one of them instead of both of them, the problem could be that you're not going to observe very significant performance improvement at the very first place, because without either QGZ or HPZ in the vanilla 0-3 scenario, you can actually like the actual time you spend on doing the two different collectives during backward pass actually doesn't change that much comparing to just doing one single collective during the backward pass. And so in this kind of scenario, where to conclude, if you are using Ethernet and single TCP flow cannot saturate your Ethernet bandwidth, and you have already enabled prefetching in DeepSpeed, then our conclusion will be that it's better to enable gradient quantization and also hierarchical parameter partitioning altogether to actually get the best performance out of it. And regarding the result, we'll just briefly talk over the like relative difference. And I think after enabling 0++, and we see the overall throughput performance is like 2.4x is 2.4x is comparing to using vanilla 0.3 on one of on one of the like open source models that we were benchmarking on. And regarding the scaling part, again on the commodity hardware that we were using to test the performance, and we also were able to notice that by enabling 0++, since that the cost for internal connection is much less, and the scaling factor can significantly increase a lot comparing to just using vanilla 0.3. And yeah, I think that's all regarding what we've done regarding 0++, and I think it's really a smart algorithm that's able to like optimize the internal connection, the throughput by improving three different collective operation in 03 separately. And yeah, that was a very good experience doing some debugging and improvement on that. Yeah, it's tokens per second, and I'm not sure if we are able to disclose the actual magnitude of the throughput, so we just mask it out. Sorry, could you repeat? Okay, so the question is, it doesn't look like a linear increase even with 0 plus plus. And that reason is because if you are using a, say, for example, commodity hardware that has a very low Ethernet connection, then from scaling from one single node to two nodes, it's very likely that your overall throughput, by overall aggregated throughput can decrease, because by going from purely internal connection, probably you have NVLink, to going to having to be bottlenecked by the Ethernet connection, your step time can increase by some number larger than larger than the time your global batch size increases. The question was, why does the overall throughput drops from scaling from one box to two box using zero stage 3? And yeah, the answer is just exactly the same. Like, say, for example, if you are using some hardware spec that that doesn't have a very high throughput interconnect between nodes, then like like I can elaborate a little bit. Like when you're using just a single node, for example, if your global batch size is X and your whole throughput in terms of step time is like 1 second, but if you scale it to two nodes, even though your global batch size gets increased to 2x, but your step time gets increased to like 3 seconds, then the overall throughput will actually be decreased, because you have to be bottlenecked by the internode Ethernet connection. I can take one more. What was the question again? The result from using LoRa. Loss. I don't think we prepared the plot for this particular slideshow. You mean the gradient quantization? It's not similar to QLoRa. It's like pretty much just doing a block-based quantization of the gradient, and you are communicating on the 4-byte integer for the reduce gather. Yeah, but still, like the difference can also come from like if you're doing full parameter fine tuning or just LoRa based tuning, right?
Yeah, it's mainly because we want to do full parameter fine tuning. So even if we can get the same result from QLoRa, but we want to see how the performance is like for full parameter fine tuning.
Yeah, we can take one more question. You can go ahead. Yeah. Yeah, I would phrase that into more of an algorithm decision choice. I guess maybe Tanji can also elaborate that a little bit in later. But that's also largely because considering this kind of framework based on this kind of algorithm based on 0-3 already, and you want to optimize it in different 3 parts, like the forward altogether, backward altogether, and also the gradient synchronization. Well, there's definitely some better approach comparing to just say, for example, if it's for sure, probably we can also do like a quantized parameter synchronization for backward pass, but it's just gonna be better if you can just like completely nuke the internal connection during backward, if that's possible, right? Because, for example, if you, even though you reduce the pay workload by half, it's still not going to outbeat the gain from just doing the connections purely intranode.
So if I understand correctly, the question is why are we doing int8 quantization for the weights and int4 for the gradients? Is that correct? Yeah, yeah. Right. 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 And specifically when we say backward, we mean the gradients. So right, yeah. So it's because the number distribution for weights and gradients are different. And so what we did was we did a study of the distribution because weights and gradients are different phenomena. And we found out that you know, gradients are easier to quantize into low precision compared to weights. Yeah, yeah.
Okay.
Well,
Oh. Yeah, we do enable that.
Okay.
Yeah. Okay. I think that's pretty much all. And thanks everyone.
Just one quick plug. You heard about all the great work happening, right? And places we are contributing. We're also hiring, right? So just want to make sure you're aware, right? Reach out to any of the folks, like, you know, who are talking here, or even to Tunzi, right? Like he can get the right folks to us as well. So.
All right, next on stage is Kifa.
Good evening. My name is Kiefer, and I'm from Intel. Online, there are a few of my teammates. They're Guokai, Roger, and Koichi. And today, we're here to talk about our work with Microsoft to use DeepSpeed to speed up LLM models on Intel devices. So you might wonder, what kind of devices do Intel have that you can run deep learning models on, right? Intel actually added support for AI models in our different processors a few years back. We have the CPU, this Xeon CPU, the 4th gen and the 5th gen Xeon CPUs have built in these advanced matrix extension instructions that can be run on these TMAL hardware. TMAL is can operate matrix multiplications at a tile level, because usually when you look at instructions, for instance, AVX instructions, they operate computations at the 1D vector in 1D vector registers. With TML, you're actually doing these computations on 2D registers. So it greatly accelerates matrix multiplications. And we know that matrix multiplications is one of the most used operations, mathematical operations in deep learning. So Xeon processors has AMX instructions. Our GPUs, which our first generation data center GPUs, which we launched maybe a couple of years back, also have hardware dedicated for AI. And the GPUs was designed mostly for HPC apps as well as AI applications. The XC cores support the XMX instructions, which are again matrix multiplication acceleration instructions. And these GPUs are deployed in national labs. The Aurora cluster, for instance, Cambridge, and the LRZ cluster. And then thirdly, we have built a AI specialized AI accelerator, and it's called the Gaudi 2. And these are have also matrix multiplication engines called MME, and these again are accelerators for matrix multiplications. And in addition to that, there are these TPCs, right? The tensor processor core that are in these Gaudi 2 processors as well. And these are programmable. It means that they can be used to run, to execute operations that are found in models that are not matrix multiplications. So what we have these devices that can do AI. And one of the things that we wanted to do was be able to use DeepSpeed on these devices. But when we started looking at that, we realized that at that time, DeepSpeed only supported CUDA devices. So what do we have to do? We had to go and talk to Microsoft. And fortunately, the DeepSpeed team at Microsoft, particularly Tunji, was open to discussing with us and opening up DeepSpeed to support other devices. And on the right side here, I guess, is sort of the stack, very simplified stack of what it looks like, right, to be able to run DeepSpeed on Intel hardware, and actually any hardware. So there is the DeepSpeed layer at the very top, and then there is DeepSpeed calls into PyTorch, and Intel has actually been adding a lot of code inside PyTorch to support Intel devices. And in addition to the PyTorch framework, Intel has also what we call the Intel PyTorch extension. This is an extension of basically a Python wheel file that you can install. And this is where we add in the bleeding edge optimization and features, latest features. Over time, we intend to contribute directly into PyTorch and do away with PyPacks, right? So we don't have to there won't be a lag from using the latest features or the latest optimizations if you don't have PyPacks. And underneath that, you can use different training infrastructure that support different hardware. You got CPUs, GPU in these clusters, Azure, for instance. So what did we do? We basically had to design and device agnostic API in DeepSpeed. And so we designed it with the DeepSpeed team, with Tunji in particular. And then this is to abstract the common hardware features that we find in accelerators. So with this accelerator API, this sort of an abstraction layer, new hardware can be enabled on DeepSpeed by implementing this layer, the API underneath it. And models, DeepSpeed models can be written to be hardware agnostic, right? You don't necessarily just have to write it for CUDA devices. You can write this using this API and be able to run it on different types of hardware. So we feel like with this accelerator, it allows for more flexibility in deploying solution cloud clusters, right, with different accelerators, and end users basically just have to write one DeepSpeed model, optimize one DeepSpeed model, write one script that utilizes DeepSpeed, and be able to deploy it across different hardware. And this is an example of what a developer would have to do, right, to use this accelerator interface. Basically, you have to import this module called DeepSpeed Accelerator, and then instead of calling, what you usually do is call, like for instance, that get is available function. Usually you say torch.cuda is available, but instead of doing that, you just replace that with get accelerator is available. So that's typically what you need to do to use this more device agnostic or hardware agnostic API. So I think the main goal here is to open up, DeepSpeed to support different hardware and give choices to developers, and to allow hardware vendors to be able to utilize DeepSpeed, which is a great library. So one of the features in DeepSpeed is the auto TP, and I just want to highlight that this is one of the features that we have enabled for DeepSpeed inference to support distributed large language model, and we have extended auto TP support in additional Hugging Face models, and here are the models that we have added support for, and we'll continue to add more support for more models over time. The key thing here is, model changes are not required, and you can just use it on, Intel hardware. So again, the message is, you customize the optimizations for performance in the model and in your script, and then you can apply it across different models, across different hardware without any code changes. So I'll, over the next few slides, list some of the examples of us using DeepSpeed on Intel hardware through this accelerator API. So this is an example of us running large LLM, basically Llama 2 and GPT-J on Intel devices, and we see on average a speed up to 1.7x using DeepSpeed, going from single socket to dual socket. And this is a great example of us using DeepSpeed and be able to leverage DeepSpeed to get performance gain. So, excuse me. So you may wonder, who is using Intel GPUs? Actually, the Intel GPUs are used in national labs, the Argonne cluster, and they have used this to do training, trillion parameter training Megatron. I'll give more information about this particular cluster in the next foil. And then the Cambridge cluster is also using Intel GPU Max on GPT-3 175 billion parameter model to train that model. And then another lab is called, it's the Leibniz Supercomputing Center. They are also using DeepSpeed on Intel GPUs to train this very large model. So last year in Supercomputing 23, Argonne announced they had successfully used DeepSpeed on Intel GPU to train trillion parameter LLM, and they have tried using model parallelism and data parallelism, right, to train these models. And the target is to be able to use 10,000 nodes and in the future, and that work is going on right now. So this cluster, this Argonne cluster, Aurora cluster, will be used by researchers in the US and maybe in the world as well to do model training using these GPUs and using DeepSpeed for their research, right? To be able to apply AI and use AI models in their research projects in systems biology, cancer research, climate. So we're very excited about this potential applications, right? To be able to use them in these applications. So that was Intel GPU. Oh, sorry, you have a question. Model dot. Okay, you mean that the accelerator dot API. Oh, so what we had to actually enable kernels inside DeepSpeed as well as inside PyTorch. So in the back, right, as hardware vendors add support in DeepSpeed for their hardware, there is an implementation that hardware vendors have to do. So, but we follow the accelerator interface API so that it's standardized across. It makes it easier for developers or end users to be able to say, okay, I want to use DeepSpeed. I just write one code or optimize model using one way, and then be able to use that same code across different devices. But in the back, yeah, it's not free. Basically, the hardware vendors have to go and implement in the back to support these. And the work, we have started the work and we'll continue to do that work, right? Because there's a lot of, DeepSpeed is very rich, so there are a lot of features that we want to enable as well going forward. Gaudi 2 is a accelerator that was designed specifically for AI. This is not a GPU. It's dedicated for AI. And in fact, last year when we submitted our GPT-3 data, training GPT-3 performance data to MLPerf, it was one of only 2 devices out on MLPerf that have GPT-3 training numbers. The other one was a CUDA device, as you could imagine. So again, we enabled DeepSpeed to be able to use Gaudi 2. And these numbers that I'm showing here are from the MLPerf submissions that Intel has submitted. So yeah, so we're pretty happy that we are offering this, and it has DeepSpeed support as well. Okay, so in summary, I hope that I have conveyed to you and convinced you that the value of this layer, this API, accelerated API layer, because from our point of view, it opens up DeepSpeed, which is an open source library, to be able to support even more devices. Right now, Intel has added support to CPU, GPU, Gaudi, and we have actually noticed that there are other hardware vendors adding support as well. I think the MPS and MPUs are from our other hardware vendors. So hopefully over time, that support will increase and will make DeepSpeed an even more popular devices library that can be used across different devices. And the main selling point here is, I think, as a developer, you basically just have to optimize your model once using DeepSpeed and then write the script to use DeepSpeed and then be able to deploy that model, the optimized model with that optimized script across different devices on the cloud, and not just be focused on just one or constrained to just one type of device. And okay, so we've also said that we'll continue to support DeepSpeed and optimize app features and make DeepSpeed work better on Intel devices. And I'm very happy to be able to say that we've done a lot of that work, and we're very we really enjoyed the work we've done with the DeepSpeed team at Microsoft. Thank you for listening to me, and also I want to thank LinkedIn for hosting us, and also Tunji in particular for inviting us to speak. Thank you. Any questions?
All right. Thank you, Kiefer. This will be the final talk for today. And so I'm going to briefly talk about our inference solution called FastGen. So FastGen, from a user perspective, comprises of two components. The first one is the DeepSpeed MII, which is basically an inference server solution. And it allows the FastGen inference, and it supports the FastGen inference engine. Then the FastGen as an inference engine is something you can think on the line or similar to like a VLLM or TensorRT LLM that accelerates generative AI. So FastGen provides 4 key optimizations: continuous batching, dynamic split fuse, which I think is unique to FastGen. We have CUDA kernels, and we have the block KV cache, which is basically similar to the paged attention technology in VLLM. In terms of how the software stack is laid out, you can see there with different colors. The key thing I want to just highlight here is that at DeepSpeed, we build our solutions to be very modular and pluggable. So we're very open source. We're very community focused. So we make it possible for researchers and hobbyists to create their own components and plug into things we've built. And so here we have both the FastGen optimizations. We are using things from Hugging Face. We're building kernels as well. And in terms of the models that we support a large number of models, including the famous ones you know about, like Llama, Mixtral, and Phi. So if you are a user and you wanted to use FastGen, there are 2 key APIs that you need to be aware of. We have an API which we call the persistent deployment one. This is the high performance one that you want to use if you're deploying a long-running inference solution in production. Right? And this one basically comprises of a server and a client interface. So you set up your server once, and then you can set up clients that send queries or requests to it. But for quick debugging, we also have something called a non-persistent deployment, which you can just run in a single session or a single, in a single process, essentially. And this just sets up both the server and the client in the same process. And that's great for debugging or for quickly getting started. So let's just take a step back to what is the challenge with generative inference, right? It's not, when we think about inference, you can think about it as just running a forward pass, like, as you would do when you're doing your validation or evaluation of your model. But generative inference is actually different, and that kind of makes it interesting. So in text generation, there are basically 2 distinct phases. One is the prompt processing. So your client or your user sends you a prompt. You can ask, what is the meaning of life? That is the prompt, right? And so your model initially has to process that, and then starts giving you a very, very lengthy answer about the meaning of life. And that part where it's giving you the answer is what we call the decode phase. So this is where it's basically trying to give you something meaningful that hopefully gives you an answer that you like. Now, from a systems perspective, these two phases have very different properties. The prompt phase basically is like, like I said, the prompt could be very long. You could throw a textbook at it and tell it to summarize a textbook for you, just to be very extreme. And so from a systems perspective, that one typically has high efficiency because the data is very large, right? Its prompt length is large. There's a number of gems running in the background. The large gems are very good for efficiency. But the decode phase, essentially, it's generating one token at a time. It's looking at the previous token and generating one. And so you are essentially bottlenecked. You become memory bound because the amount of compute work is much lower than compared to the prompt phase. And so, and then there's the other aspect of it is when you're deploying this as a service, you can't afford, so the tricks we typically play in training when we have low efficiency is to bump up the batch size. But with inference service, you can't afford to do that because your customers are waiting for a response. You can't afford to wait for enough people to show up so you have a large batch size. And so the question of how do you do scheduling, how do you do batching is a big one in this space. And currently, what is sort of the state of the art is to do scheduling at the iteration level. So in between each forward pass, you get a chance to either take in a new request and do the prompt for it, or you continue decoding the request you had previously. And so VLLM, which is the state of the art technique, actually does this. And what they do is, as I'm showing here, is so if you think of time going from left to right, is we are in the middle of some decode, right? And then a request comes in. And so what VLLM will do is we will sort of preempt the decode, bring in the prompt to process it, then go back to the decode. Now, from a user perspective, from a user perspective, this is good because the new prompt, you get the first response right away. So like the system is being responsive to you. But if you were the ones who had your request in there before, now you have a delay because now some prompt has gone in and bumped you off. And eventually, so if you've seen VLLM results, typically the time to first token is always great because they preempt whatever they're doing to prioritize the prompt that just came in. And so the time to first token is good. But the time to the other tokens or to the last token then suffers, right? Because every time a prompt comes in, your decode gets preempted. And so that's from the user perspective, right? There's a good and there's a plus and minus to it. But from a system perspective, there are two things to show up here. First is you can see that we're spending a lot of time doing decode. And like we said earlier, that is inefficient from a systems perspective. Then secondly, the latency of your decode gets affected every time a prompt shows up. And so those are like the two key challenges that the current techniques have. In looking at this problem, we analyzed the workload and came up with two key observations that led to our solution to this problem. The first observation is that your latency for a forward pass is actually not so much dominated by the batch size, the number of batches you have, but rather by the prompt length, the token length. And so that's what we're showing here. The x-axis is showing the token length and the y-axis is the latency. And then we have different colors there. All of them are bunched up. They're from batch size 1 to 8, just basically showing it doesn't matter which batch size you are using. It's the length of the prompt, the total number of tokens that really determines the latency. And so what this means is, like we said earlier, right? Like if you're doing generation and a prompt shows up and that prompt is very long, it's going to like penalize your generation because it's going to take a long time for that prompt to get processed, right? Before you can resume decoding. The second observation is that, like I said, high token counts helps. But eventually it saturates. Like so the more you scale up your token length, and that's what we're showing here. X-axis is still number of tokens. Y-axis in this case is T-flops, just showing basically your hardware efficiency. Yes, as you scale up, there's more work, hardware is more efficient, but eventually you hit some saturation points, like it never grows forever. And what this tells us is that, well, we could actually limit the token length without hurting efficiency too much. So maybe that's sort of giving you an idea of where we're going here. So we came up with a technique called dynamic split fuse, where we're able to compose, prompt, and decode. And I'll go into a little bit more details about how we do that. So now, instead of having distinct phases of prompting and decoding, we actually compose them together. And to be able to do this, we kind of like first come up, I'll just go back for a second, right? So that point there that I circle is sort of like a good prompt length for which you get close to the best hardware efficiency. So let's call that the target forward size, right? So we just want to always ensure our prompt length is basically at that size. And there are a number of ways we can achieve that. One is we can take, when a very long prompt comes in, we just split it up and break it up into multiple prompts, all of that size. And what we showed earlier was that it doesn't matter how long it is, the latency is still going to be the same, right? If you take a long prompt, you break it down into smaller prompts, the latency across it all will be the same, so you don't actually get hurt there. Or we can take short prompts and compose them together, and so that we can process the prompt together, high efficiency. And then this also allows us to combine decode. So things that are in the decode phase, we can combine them with existing prompts. Now with split fuse, then we are now able to do continuous decoding. We never, ever actually stop decoding, which means that the requests that were already in the system, they don't get penalized when a new request comes in. And so this is sort of what that looks like. So we're showing here that you have a decode initially, then a prompt comes in, and so we just combine them together. A request comes in, we combine the decode with the prompt with the ongoing decode, and then we continue. And so here we've taken that prompt that came in, we've split it into sort of the target size, the target forward size, and then combine it with the decode request, and then we're able to sort of do that. And so the point is that even though we've split this prompt into three, the end-to-end latency actually is roughly the same. But the benefit is that the decode that was going on, the users are getting their response at the same time without any delay, and then we get to the phase where we're doing decoding. And so this is sort of the key idea here. So how does this look in terms of performance, right? And so I'll just highlight two results here. We have a lot more in our blog that we released in February. And so I'm just going to show results for Phi-2 models, the 2.7 billion parameter model, and then the Mixtral 8x7B MOE. And what we're showing here is both, when we look at benchmarking here, we don't look at just one of either latency or throughput, because in real scenarios, both of them matter, right? Like latency, users care about end-to-end latency, so that's like an SLA guarantee. The cloud providers or hardware owners care about throughput. They want to utilize their hardware efficiently. And so the plot on the left is showing here, we're comparing against VLLM. And what we're essentially showing here is that, as you increase, and so here for this request, we sort of run up to 32 clients, all throwing in their requests over time. So it's trying to simulate like a real production scenario. And so as the x-axis is showing the throughput in terms of queries that are completed per second, the y-axis is latency. And the reason why the curves all look that way is that as you increase the load on the system, eventually, systems kind of saturate and your latency starts to shoot up. But what we're just showing here is that if we had, for example, an SLA of like 2 seconds, at that point, FastGen is given a 2.5x higher throughput than what you would get with VLLM. Similarly, with the Mixtral, which is on the right-hand side, it's about a 2.4x, and the target latency here is about 3.5. You can get the higher throughput. And this is really, and when we talk about throughput here, we're talking about the time to finish the generation for each request. And so then this is coming because we are not delaying the generation, right? We're just combining incoming prompts with it and not delaying it. Okay. So then another improvement we've made to FastGen is to explore quantization. And so this was, we released this about a couple of weeks ago. where we basically do FP6 quantization of the weights. So just an overview, like why FP6 and not int4? We found out through a lot of studies that, for downstream tasks, int4 can have some performance degradation, while FP6 is sufficient to sort of recover most of that. And so we're showing some code generation and text generation numbers here. We have blogs and archive papers that you can refer to for more details. But the challenge with FP6 quantization, as you can imagine, is that that is not a power of 2. And so hardware vendors typically optimize things that are power of 2. So how can you do this efficiently? I won't go into all the details here. We also have a paper, a systems paper for that. But the trick there basically is to break this down into a 4x2 kind of package formats. Right? And so that way you can represent both the 4 and the 2 bits are things that are powers of 2 and can be efficient on hardware. And then we did some gem, kernel gem evaluation, and we found like some good speed ups with this formats. So, the first benefit is memory, as you can imagine, right? Going down to FP6, and that one of the cool things about that now is that you can take a 70B model and inference it on a single GPU, which is, absolutely amazing, right? Because now it's like less than 1 bit, less than 8 bit, and so yeah, that sort of numbers break down here. That's kind of exciting. But also we did see some benefits also in terms of the throughput latency. And so here we're comparing against our DeepSpeed FastGen with FP16. And here we're seeing like both on the throughput and latency, we're seeing benefits. And this is really coming from the fact that, as you can imagine, since we've the memory bandwidths of, in the GPU of actually fetching the data in and doing the compute makes for much faster execution. All right, and so I'll just sort of wrap up there in terms of our future work. We think we're very excited about FastGen. We've made some great results compared to state of the art, and we think there's a lot more that we can do here and offer to the community. It's basically our newest line of work, so it's still there's still a lot of growing for us to do here. And so our future work is basically focused around that. We're looking at performance improvements. We have more optimizations to come. We want to increase the coverage. We cover a fair number of models now, but we're looking to extend that. Right now, on the accelerator side, we're still very much CUDA kernels. So it's typically what you have to do when you get started, but we are looking to our partners as well to work with them to extend this to other hardware. That's something that we're very excited about. Yep, quality, stability, all of that. We welcome your issues. Please open issues as you try this out, and if you run into problems, please open up tickets, or better yet, send PRs. We are very welcoming to both. Yeah, and that's all I have. Thank you very much. GitHub is, we are open sourced on GitHub. We absolutely love contributors. It's a community, and DeepSpeed has grown because of the community. So we're excited to be here, to be with to see the support of the open source community. And that's all I have. SRT, I don't believe we have any numbers on that yet, but I think we should probably do that. Yeah. Yes, please. No, we maintain their different KV caches. So even though they're like, the prompt has its own KV cache, its context that's processing on, the decode has a different context. So they don't mix, we don't mix that. Yeah, it's the same, right? Because they maintain different contexts. Yeah, yes. We do have a line of work along those lines in terms of, yes, like the scheduler, the deployment optimizations. Yes, we do have a line of work there. Let's see. I guess it depends on your scenario and what kind of performance you're aiming for. But yes, from a usability, it's easy to set up and tear down. It's using gRPC at the baseline, so I don't know like what kind of SLAs you are interested in. But please try it out, and if you whatever you see, please share with us.
Another technique is like speculative decoding with like graph
Yeah.
models. So like, do you think, are you planning to combine that with the split fuse? And in your comparison, is it already faster than split fuse?
Oh no, we've not evaluated speculative decoding, but I think that's a very interesting idea. It's not something we've got into, but it's certainly on our roadmap to look into that.
Great talk.
Thank you. Oh no, we just split the tokens. Like if it's 1,000, it's a 124K token, and 512 is our target. We just cut it in half. Yeah. No, it shouldn't. As long, in terms of the computation itself, it's no different, right? Like because as long as we're not carrying any context, we know when we're in the prompt phase, and so we don't carry any information over into the next prompt. Like so, this next prompt half, if I put it that way. So we only do generation when we actually have looked at the entire prompt. So yeah, so we're just basically computing the KV cache, which is like, yeah.
So a follow-up question regarding the split of the prompt. So I think that you have to calculate the self-attention between different tokens of a single prompt. Now, if you split into 3 parts, how do you make sure that the tokens in the first part can attend to the tokens in the second and third part?
That's a great question. So we are not doing cross attention. We're only sort of doing self attention, where you only attend to the tokens that come before you.
So you mean it's for the prompt?
Yeah, so the question is like, how do we, if your tokens are attending to tokens after you, right? Like, so we're not considering that. We're only considering the ones where of the tokens where you attend to tokens that come before you. So I think that's more like the simpler attention mechanism.
And a token in the second part needs to attend to the another tokens in the first part.
Yeah, yes, but then the KV cache is already available at that point in time.
Okay, I see.
Yeah. All right. Thank you. Thank you very much, everyone, for coming. We're really very grateful for the show of support. This ends the presentation part of it, so I think we can move to sort of the networking and the more informal part. Thank you so much.